This call is now being recorded.
Okay. Good morning, all. So today we'll start with the last type of the chapter number 2, that is the strain energy. So in the last lecture, we have covered the problems based on the impact loading, that is type number 3. So in that particular type number 3, we have discussed how to solve the problem based on the impact loading condition and how to identify that particular statement, whether it is based on the gradually applied load, suddenly applied load, or the impact load. So in order to identify the problem related to the impact loading, so we have to read that particular statement carefully, and you have to check that whether the falling height is mentioned, whether movable load is mentioned, or sometimes the rod which is connected to the collar, like that words are mentioned, or sometimes the impact loading, like that words are also mentioned in the statement. If such types of the words, common words, are mentioned in the statement, then we can say that that particular numerical is based on the impact loading. So whatever the three numericals we have solved in the previous lecture, in that the first numerical we have solved related to the impact loading. That means if any load is falling from the certain height, due to that load, how much amount of stress and how much amount of elongation is taking place. That one problem we have solved. Then in the second problem, the load is given, the stress is given, and we have calculated the falling height. So whatever the movable load is strike on the collar, that falling height we have calculated in the second problem. And the third problem we have calculated related to the unknown weight. So in that the deformation is given, that is elongation of that particular collar or the elongation of rod, it was given in that particular numerical. In addition to that, the falling height, it is also given, and by using the deformation formula we have calculated the stress induced in that particular rod, and then by using that particular stress we have calculated the unknown weight which is falling from the certain height. So whatever that unknown weight is calculated, we have calculated by using the two formulas. Either we have used the sigma formula, sigma is equal to P upon A in square bracket 1 plus square root of 1 plus 2h upon delta L. This formula also we can use, or otherwise we are having the second formula also, which one? Strain energy is equal to work done. So I hope everyone has solved that particular numerical by using the both formulas. And if you solve that particular problem, or if you obtain that unknown weight by using both the formulae, your answer will be same, that is 5 into 10 raised to 3 Newton. That means you will get the answer, that is 5 kilonewton. Okay, so that type number 3 we have discussed in the last lecture. Now we'll discuss about the last type of this particular chapter, that is problems on last type of this particular chapter, problems on strain energy, problems on strain energy for varying cross-sectional area. Problems on strain energy for the varying cross-sectional area. So such types of the problems, bars of varying cross-sectional, we have covered in the chapter number 1 related to the deformation calculation. So same structure is there, but here the somewhat unknown parameters are different. So what is our requirement in this particular type number 4? We have to calculate the total strain energy stored in this particular bar. Up till now, whatever the problems we have solved in the type number 1, type number 2, and the type number 3, in that whatever body is considered or whatever the body is given, that body will be the single body. That means only single bar is given. So whatever the strain energy we have calculated, that strain energy we have calculated for the single bar only. But now in this particular type number 4, we have to calculate the strain energy stored in the each and every section, because if you go through the construction here it consists of a total 3 sections. Section number 1, then section number 2, and the section number 3. All the 3 sections are rigidly connected to each other, and all the 3 sections are having the different cross-sectional area, because if you go through the section number 1, diameter is different, section 2 diameter is different, section 3 diameter is different. Therefore all the 3 sections are having the different cross-sectional areas. Therefore this particular structure is called as a bars of varying cross-sectional area. And this particular section, it is subjected to the external force P. So whatever the P amount of force is applied externally, same force we have to consider for section 1, section 2, and section number 3. Now in this particular type number 4, I have to calculate the total strain energy stored in this particular bar. So we are having the simple formula, strain energy is equal, we are having the simple formula, energy is equal to sigma square upon 2E into volume. So this formula is applicable for the single section. So whatever the U is given, U is equal to sigma square upon 2E into volume. Sigma means stress induced in that particular section. Volume represents the volume of that particular section. So up till now, we have used this particular single formula for the calculation of strain energy in the single section only, because whatever the bar is given in the type number 1, in type number 2, in type number 3, only single bar is given. So we have used this particular formula for the further calculation. Now in this particular type number 4, we have to use the same formula to calculate the total strain energy stored in this particular section. Suppose I will give the name A, B, C and D. So AB represents section 1, BC represents section 2 and CD, it represents the section number 3. If I have to calculate the total strain energy in the bar AD, the total strain energy in the bar AD, so we are having the formula, the strain energy stored in the section AB plus strain energy stored in the section BC plus strain energy stored in the section CD. So if I will make the addition of the strain energy stored in all the three sections, it will give the total strain energy stored in this particular bars of varying cross section. In the chapter number 1, we have calculated the deformation. If I have to calculate the total deformation of this particular bar, what I have done, I have calculated delta L1 for the section 1, delta L2 for section 2 and delta L3 for the section number 3, and for the total deformation is equal to delta L1 plus delta L2 plus delta L3. This formula I have used for the total elongation calculation. Similarly, in the strain energy calculation, if I have to calculate the total strain energy stored in the section AD or bar AD, what I have to do? I have to do the addition of the strain energy stored in the section number 1, section number 2 and the section number 3. Therefore, U of U of AB means strain energy stored in the section number 1 or section number AB. U of BC means strain energy stored in the section BC or section 2, or U of CD, it represents the strain energy stored in the section CD or section number 3. Therefore, U of AD is equal to, U of AB means we are having the sigma AB square upon 2E into volume plus U of BC means sigma BC square divided by 2E into volume plus U of CD means sigma CD square divided by 2E into volume. So only change is that we have to change the stress value only. While calculating U of AB, consider the stress induced in AB section. While calculating strain energy stored in the BC, consider the sigma of BC. And while calculating the strain energy stored in the CD, consider the sigma of CD. To calculate the volume, we are having the formula area into length. So for the first section, area is available, length is available. For the second section, area is available, length is available. Similarly, for the third section, area and the length are available. Remaining part E is the constant parameter. If all the three sections are made by the single material only, this E will be common. If section 1, 2, 3, if all the three sections are made by the single material, for example, steel is used, then we can take this particular E as a constant parameter. So this is the type number 4, which is related to the problems on the strain energy for the varying cross-sectional area. In the chapter number 1, we have used this particular structure for the calculation of total elongation or the total deformation of bar. Now here the concept is same, but instead of calculating the total elongation, here we are calculating the total strain energy stored in that particular bar, which is equal to summation of strain energy stored in the each section. Now here the three sections are given, therefore U of AB plus U of BC plus U of CD. If only two sections are given, then U of AB plus U of BC. It depends upon the number of cross-sectional areas given in that particular statement. So this is the simple formula, that is to calculate the total strain energy stored in the bars of varying cross-sectional area. Okay, so this is the theoretical part, or this is the formula. There is no any modification, only we have to use this strain energy formula 2 or 3 times according to the number of sections given in the statement. Okay, so this is the theoretical part. Now based on this, now we'll solve a one numerical. So the first numerical is in front of you. So I will read the statement and then we will solve it. A maximum stress produced, if maximum stress produced, the maximum stress produced if the pull in the bar of length, the maximum stress produced if pull in the bar of length 1 meter. Total length of bar is given 1 meter and that particular bar is subjected to the maximum stress and its value is given 150 Newton per mm square. The maximum stress produced if pull in the bar of length 1 meter is 150 Newton per mm square, full stop. The area of cross sectional and length shown in the figure. So whatever the cross sectional area is there, that cross sectional area or their length, it is shown in the figure. That means figure is given to you, full stop. Calculate the strain energy in the bar. Calculate the strain energy in the bar. Take E is equal to 2 into 10 raised to 5 Newton per mm square. Take E, it is a constant parameter, only one Young's modulus is given, means whatever the number of sections are given for each and every sections, we have to give the same Young's modulus. Now if you go through this particular construction, in the construction, whether the screen is visible to all? Whether the figure is visible?
Yes, sir.
Yes, sir. Yes.
Okay. So if you go through this particular figure, the figure is given like dumbbells. So whatever we are using for the exercising. So the figure is given in the form of dumbbells. So the AB, then BC and CD. Okay. The section number 1 having the cross sectional area 200 mm square. Section number 2, that is BC section, having the cross sectional area 100 mm square, and section number 3 CD, again the cross sectional area 200 mm square. Section number 1 is having length 475 mm. Section number 2 having length 50 mm, and again section number 3 475 mm. That means the section number 1 and section number 3 both are similar to each other. Whatever the cross-sectional area is given for the section AB or section 1, same cross-sectional area is given for the section CD or section number 3. You can see 200 mm square, 200 mm square. Similarly, length of section number 1, 475 mm, length of section 2, 475 mm. But what about middle section? Its cross-sectional area is 100 mm square and its length is given 50 mm. Okay, and total length of this particular section is 1 meter. If 475 plus 50 plus 475, the total length of this particular section is 1 meter, or it is equal to 1000 mm, which is given in the statement. And this particular section, section 1, section 2 and section 3, that means this particular bar AD, it is subjected to the maximum stress of given. I will write down the given. It is subjected to the maximum stress of 150 Newton per mm square. Only one stress is given and the word is given maximum stress. Okay. Then capital E is equal to 2 into 10 raised to 5 Newton per mm square. And we have to calculate the total strain energy stored in the bar, that is U of AD. We have to calculate. Now, I will ask one question. Whatever the maximum sigma max is given, this sigma max is applicable for section number 1, section number 2 or section number 3. Please tell me the answer. Whatever the sigma max, maximum stress is given, whether it is applicable for section number 1, section number 2 or section number 3. For which it is applicable? use the concept in the chapter number 1. It is not applicable for all the 3 sections. It is not a load, it is stress. Here 150 it is given. It is not a load, it is a stress. Yes. Apply the concept from the section number 1. The stress is maximum where area is minimum. Stress is maximum where area is minimum, and stress is minimum where area is maximum. Now here the maximum stress value 150 Newton per mm square it will be given. Now out of the 3 sections, where the area is minimum?
BC.
Yes. In the section BC, if you compare all the 3 sections with each other, section number 1 and section number 3, all are having the same cross-sectional area, 200 mm square, 200 mm square. Their length are also same. But if you think about the section number 2, it is having the cross-sectional area 100 mm square. If I will compare section BC with section 1 and section 3, if I will compare this section 2 with section number 1 and section number 3, this 100 mm square is less than 200 mm square. That means for the section 2, the area is minimum, means we can say that whatever the sigma max is given, that sigma max is equal to sigma of BC is equal to 150 Newton per mm square. Why it is like that? Because area is minimum for section 2 or BC. Getting why this 150 Newton per mm square will be considered for the section BC only? By applying the concept, the stress is maximum where area is minimum, and from the figure we have observed that for the second section or for the BC section, the area is minimum how much? 100 mm square. Therefore, whatever the sigma max is given, that sigma max will be applicable for the section BC. Therefore, sigma of BC is equal to 150 Newton per mm square. Now, by using this particular sigma of BC, I have to calculate the stress induced in section number 1 and stress induced in section number 3. If I will calculate for the stress induced for section number 1, same stress will be applicable for the section number 3, because section 1 and section 3 both are similar to each other. Now, how to calculate the stress in the section 1 and section 2? Because to calculate the strain energy stored in the AB, BC, CD, we are having the formula sigma square upon 2E into volume. Young's modulus is available, volume is available, but only main term sigma is not available. Only sigma of BC is given. But what about sigma of AB and sigma of CD? So initially we have to calculate the stresses and then we have to calculate the strain energy. So we are having the basic formula. We have sigma is equal to P upon A. This is the basic formula. Sigma is equal to P upon A. Therefore, P is equal to sigma into A. P is equal to sigma into A. If this P is equal to sigma into A, if I will apply this particular formula, which P is equal to sigma into A, if I will apply this particular formula for the each and every section, for example, if I will apply the sigma is equal to, because this P is common for all the 3 sections, stress is not common for all the sections, but whatever the force will be applied on all the 3 sections, this P will be common. Therefore, if the left hand sides are equal, therefore right hand sides are also equal. Therefore, I will write the equation sigma of AB into area of AB is equal to sigma of BC into area of BC is equal to sigma of CD into area of CD. Why this equation is obtained? Because whatever the force is applied on that particular section, that force will be remain same, that we have discussed in the chapter number 1, bars of bearing cross section. Whatever the force we are considering for the deformation calculation, same force we are considering for section 1, section 2, section 3. Similarly, by applying the same concept, I have written this particular stress into cross-sectional area for section number 1, which is equal to section number 3, which is equal to section number 3. Therefore, sigma of AB into area of AB is equal to sigma of BC into area of BC. I will not write the section number 3 because section 1 and section 3 are similar to each other. Now sigma of AB is the unknown parameter. Area of AB it is given 200. Sigma of BC maximum stress तुम्हाला दिलेला आहे किती 150. Area of BC 100. So I will calculate sigma of BC is equal to, do the calculation, 150 into 100 divided by 200. Therefore, sigma of AB is equal to, what will be the stress?
75.
Please check the value. How much?
75.
75. Then what will be the stress induced in the third section? What will be the 75? Therefore, sigma of CD equal to
75.
Newton per mm square. And here also your condition is satisfied. Stress is maximum where area is minimum. You can see in the section 2, area is minimum, therefore maximum stress is developed. How much? 150 Newton per mm square. But if I will think about the stress induced in AB and CD, how much it is there? 75 Newton per mm square, means the stress is minimum where area is maximum. The stress is minimum where area is maximum, that is in AB and in CD. The 200 mm square cross sectional area is given. Therefore, in that very less stress is induced as compared to the section number 2. So now the stresses are calculated. Sigma of AB is calculated, sigma of CD is calculated. Now we have to use our formula, that is U of AB is equal to U of CD is equal to sigma AB square upon 2E into volume. Therefore, sigma AB square, do the calculation simultaneously in your notebook. 2E into volume means area of AB into length of AB. So put the values. Sigma of AB we have calculated 75 square divided by 2 into 10 raised to 5 into area of AB 200 into length 475. Therefore, you will get U of AB is equal to U of CD. Calculate the value. This is the first calculation. Then second calculation, U of BC for the middle section. U of BC is equal to again sigma BC square upon 2E into volume. Therefore, sigma BC bracket square upon 2E into area of BC into length of BC. Put the value sigma of BC 150 square divided by 2 into 10 raised to 5 into area of BC 100 into length of BC, it is given in the figure 50 mm. So find out the value. Sigma of BC, how much? Newton mm. The strain energy will be Newton mm, and sigma of BC, it is also Newton mm. Just tell me the answer. Yes, U of AB 1.33, correct? 1.33 into 10 raised to 3. This will be the strain energy stored in the section AB as well as CD, because all are having the same cross-sectional area, same stress and the same length. Section AB and section CD, or section 1 and section 3, same length, same cross-sectional area, same stress. Therefore, 1.33 into 10 raised to 3. Please do the calculations. Others, please do the calculation. Then find the value of sigma of BC. 1.33 into 10 raised to 3. Therefore, U of AD, if I have to calculate, U of AD is equal to U of AB plus U of BC plus U of CD. Yes, U of CD 281.2. 281.2 Newton mm. Do the calculation for the first section AB and section CD. 1.33 into 10 raised to 3. Please check your answers. Then calculate for the section 2. 281.2. Now, if I have to calculate the total strain energy, I have to make the addition of all the three sections. So, for section AB, 1.33 into 10 raised to 3. This is for section 1 or AB plus section 2, 281.2. And again, section CD, 1.33 into 10 raised to 3. 1.33 into 10 raised to 3. So find out the total strain energy stored in the section AD. The total strain energy stored. While making the additions, we have to consider the 1.33 into 10 raised to 3 two times, because three sections are given. U of AB and U of CD, both values are same. But while calculating the total strain energy, we have to consider it two times. Yes, 2.94. 2.94 into 10 raised to 3 Newton mm. Please check your answer. The total strain energy stored in the section AD, 2.94 into 10 raised to 3. This will be the correct answer. Please understand this particular numerical here. Only one stress is given. Stress is maximum. Where stress is maximum? Where area is minimum. Therefore, sigma of BC we have considered as the 150 Newton per mm square. Then by using the formula, sigma is equal to P upon A. Whatever the force is applied, that force will be common for all the three sections. So your left hand side is equal, therefore right hand sides are also equal. Therefore, sigma AB into AB is equal to sigma BC into area of BC is equal to sigma CD into area of CD. And from that we have calculated the stress induced in AB and CD, which is equal to 75 Newton per mm square. And then by using that particular stress values, by using the Young's modulus and by using the volume of that particular section, we have calculated the separate strain energy stored in the each section. And at the end, we have made the addition. Please check your answer, 2.94. 2.94 into 10 raised to 3 Newton mm. This unit is also very important. 2.94 into 10 raised to 3 Newton mm. I hope everyone is doing the calculations in your notebook. Okay, finish. Do the calculation immediately and check your answers. Okay, so I hope everyone has done the calculation. You got the answer, 2.94 into 10 raised to 3, that is total strain energy stored. In the chapter number 1, whatever the deformation we have calculated, same concept is there, but instead of calculating the deformation here, we are calculating the strain energy. In the chapter number 1, we have used the formula delta L is equal to PL upon AE. Here, we have used the formula sigma square upon 2E into volume. Same, we have to make the addition of all the three sections and we have to find out the unknown parameters. Now this will be the last problem in front of you based on this particular chapter. So try to solve it. It is also very simple. So read the statement. A stepped bar has diameter 20 mm for the 100 mm length. Please read the statement carefully. A stepped bar has diameter 20 mm for 100 mm length and other diameter is 40 mm. Other diameter is 40 mm for remaining length 200 mm. That means only two sections are given for the section number 1. Diameter is 20 mm and its length is 100 mm. Another section is connected to the section number 1. It is having diameter 40 mm and its length is 200 mm. Full stop. The another bar up to the 200 mm. This is the case number 1. The another bar has 30 mm diameter. The another bar has 30 mm diameter and length 3000 mm. The another bar having 30 mm diameter and length 3000 mm and made by the same material. Made by the same material. Compare the strain energy of them. Compare the strain energy of them. And both bars are subjected to the load of 70 kilonewton applied gradually. Both bars are subjected to the 70 kilonewton load which is applied gradually. Please understand the statement. Whatever the first statement is given, 20 mm diameter, 100 mm length, stepped bar, another diameter 40 mm and length is 200 mm. That means one stepped bar is given. Whatever the figure is in front of you, you can see A, B and C. Section number 1 having diameter 20 mm, length 100 mm. Second section is connected to the section number 1 having diameter 40 mm, length 200. It is made by the same material. It is made by the same material means Young's modulus is remain same. Young's modulus is remain same. And this particular stepped bar, it is subjected to the external load of 70 kilonewton which is applied gradually. Whatever the 70 kilonewton load is applied, that 70 kilonewton is applied gradually, and we have to calculate the strain energy stored in this particular section AC. Similarly, one more bar is given. In addition to this particular stepped bar, one more bar is given having diameter 30 mm and length 3000 mm. This is not a stepped bar. The bar is having diameter 30 mm and length 3000 mm. This is not a stepped bar. This is the plain bar. And this plain bar is also subjected to the load of 70 kilonewton which is applied gradually. And we have to calculate the strain energy stored in this particular stepped bar also, and we have to calculate the strain energy stored in that particular plain bar also. And then at the end, we have to compare it. Now, for the first case, case number 1, what is case number 1? We have to obtain the solution for the stepped bar. So for the case number 1, we are having the figure in front of you. Two sections are given, their diameters are given, their lengths are given, and it is subjected to the load of 70 kilonewton which is applied gradually. Means by using this particular 70 kilonewton load, I can calculate the stress induced in the section number 1 and stress induced in the section number 2. Now, first of all, we will calculate we will do the calculation for the section number 1. Now, case number 1, strain energy stored in stepped bar. Strain energy stored in the stepped bar. So stepped bar is in front of you. The two sections are given, section 1, section number 2. So if I have to calculate the stress induced in the section number 1, if I have to calculate the stress induced in the section number 1, we are having the basic formula, sigma is equal to. Now here, please tell me which formula I have to use. Whether I have to use the sigma is equal to P upon A, or whether I have to use the sigma is equal to 2P upon A. Please tell me the answer. Which formula I have to use, P upon A or 2P upon A?
P upon A.
P upon A.
Why?
Gradually apply.
Yes, whatever the load is applied, 70 kilonewton load is applied, that load is applied gradually, and for the gradually load applied, we are having the formula, remind that particular derivation, sigma is equal to P upon A. So by using this particular formula, initially I will calculate the stress induced in the section AB or stress induced in the section number 1. Let us see. Sigma 1 is equal to sigma of AB is equal to P. It will be remain same. 70 kilonewton load is applied for section number 1 as well as for the section number 2 also. divided by area of AB. So P 70 into 10 raised to 3. Area of AB means pi by 4 diameter of AB square. Therefore, 70 into 10 raised to 3 divided by pi by 4 into, for section number 1, how much diameter is given? 20 square. Find the stress induced in the section number 1. Therefore, sigma 2, where sigma of BC is equal to P upon area of BC, which is equal to 70 into 10 raised to 3 divided by pi by 4 into diameter of BC square is equal to 70 into 10 raised to 3 divided by pi by 4 into second diameter. How much diameter is given? 40 in the figure, or in the statement also it is mentioned 40 square. Find out the stresses induced in section 1 and section 2. What will be the stress induced in section 1 or section AB? What is the stress? Please represent your answer in the chat box. Stress is equal to force upon area. Whatever the load is applied, it is applied gradually. Therefore, we have taken sigma is equal to P upon A. If load is applied suddenly, then we will take sigma is equal to 2P upon A. Yes, what will be the stress in section 1 and section 2, or AB or BC? Yes, one answer is represented. 222.82 Newton per mm square. The stress induced in section number 1. What will be the stress in second section? Yes, second is also represented 50.70. 50.70 Newton per mm square. You can see 222. This is the stress induced in section number 1, where area is minimum. In the section number 1, diameter is 20 mm. If diameter is 20 means cross-sectional area is also minimum, therefore you will get the maximum stress. But in the second section, you will get the stress 50.70. Why? Because area is maximum, means the diameter is 40 mm. So you will get the cross-sectional area also maximum. Therefore here also the concept is applicable. Stress is minimum where area is maximum, and stress is maximum where area is minimum. Now the stresses are calculated. It is very simple to calculate the strain energy stored in the each section. Now the stresses are calculated. It is also very simple to calculate the strain energy stored in the each section. Now here the Young's modulus is not given in the statement. Let us assume that E is equal to 200 into 10 raised to 3. Assume Young's modulus is equal to 200 into 10 raised to 3 Newton per mm square. Now calculate the strain energy stored in the section number 1, that is U of AB is equal to sigma AB square upon 2E into volume, that is sigma AB square upon 2E into area into length, area of AB into length of AB. So sigma AB how much calculated? 222.82 square divided by 2 into 200 into 10 raised to 3. Multiply by area pi by 4 into 20 square into length of section number 1. How much? 100. So find out U of AB is equal to. Find out the U of AB. Similarly, U of BC is equal to sigma BC bracket square upon 2E into volume of BC, which is equal to again sigma BC bracket square divided by 2E into area of BC into length of BC. So sigma BC means we have calculated 50.70 square divided by 2E, 2 into 200 into 10 raised to 3. Area of BC means pi by 4 into 40 square into length 200. Therefore, U of BC is equal to. Yes, tell me answer. For the first section, U of AB is equal to 3.89. 3.89 into 10 raised to 3 Newton mm. Please check your answer. 3.89 into 10 raised to 3. Only few students are doing the calculations. Others, please do the calculations. I am going to check your notebooks at the end during submission. Please take care about that. Yes, 3.89 into 10 raised to 3 Newton mm. The second also calculated, I think 1.94. 1.94 into 10 raised to 3 Newton mm. Please check your answers. 3.89 into 10 raised to 3 for section number 1. 1.94 into 10 raised to 3 for section number 3. If I have to calculate the total strain energy, U of AC is equal to U of AB plus U of BC. Therefore, 3.89 into 10 raised to 3 plus 1.94 into 10 raised to 3, I will get U of AC, that is total strain energy stored in the stepped bar. Stepped bar. Make the addition. 3.89 for the section number 1, that is AB. 1.94 for the section number 2, that is section BC. And if you do the addition, you will get the final answer. Yes, 5.83. 5.83 into 10 raised to 3 Newton mm. This is the total strain energy stored. 38.9. This is wrong. Revnath, please check your answer. Yes, 5.83 into 10 raised to 3 means 5,830 Newton mm. This is the total strain energy stored in the stepped bar. As per the statement number 1, diameter 20 mm, length 100 mm, another diameter 40 mm and length 200 mm. This is case number 1. That is strain energy stored in the stepped bar. So initially we have calculated the stresses. Forces are given, cross-sectional areas are given, separate stresses are calculated. By using that particular stresses, separate strain energy we have calculated, and at the end we have done the addition, and we'll get the total strain energy stored in the stepped bar, which is equal to 5.83 into 10 raised to 3 Newton mm. Now, case number 2. As per the statement, the another bar has 30 mm diameter and length 300 mm made by the same material. That means whatever the Young's modulus is used for the stepped bar, same Young's modulus we have to use for the plain bar also, having diameter 30 mm and the length 300 mm, and both bars are subjected to the same load of 70 kilonewton applied gradually. In the stepped bar, we have considered the 70 kilonewton load which is applied gradually. Same load, same condition we have to consider for the plain bar. So here I will draw the figure. One more bar is given. This is plain bar. It is also subjected to the load of 70 kilonewton, which is applied gradually. Its diameter is given 30 mm. Its length is given 3000 mm. So for this we have to calculate. Up till now, whatever we have calculated for the stepped bar. Now this is the single diagram only. So I have to calculate. Let us consider this is the section AB. Let us consider this is section AB. Therefore, I have to calculate sigma of AB is equal to P upon area of AB. Sigma of AB is equal to area of AB, like previous one. Here, whatever the 70 kilonewton kilonewton force is applied, it is also applied gradually. Whatever the 70 kilonewton force is applied, it is also applied gradually. Therefore, we have taken sigma formula is equal to force upon A. Again, 70 into 10 raised to 3 divided by area pi by 4 into diameter of AB square. Therefore, 70 into 10 raised to 3 divided by pi by 4 into diameter is given 30 square. What will be the stress? Please do the separate calculation. This is the case number 2 for which we are calculating the stress. Yes, how much? 99.02 Newton per mm square. This condition is totally different from the case number 1. In the case number 1, we have calculated the strain energy for the stepped bar only. But in the same statement, they have assumed that one more bar is given. That bar is having the same material. Means Young's modulus is same. Also, that bar is also subjected to the same load, 70 kilonewton, which is applied gradually. Yes, sigma is 92.02. Now, calculate area strain energy stored in this plane section. Therefore, sigma AB square upon 2E into volume, which is equal to sigma AB bracket square upon 2E into area of AB into length of AB. Put the value sigma of AB 92.02 square divided by 2 into Young's modulus same 200 into 10 raised to 3. Area pi by 4 30 square into length of this section is also given 3000. Therefore, U of AB, which is equal to uniform bar. Uniform means plain bar, which is equal to. Yes. What will be the answer? 51.98 into 10 raised to 3 Newton mm. Please check your answers. 51.98 into 10 raised to 3. This is the strain energy stored in the uniform bar, and whatever the previously we have calculated 5.83 into 10 raised to 3. This is the strain energy stored in this stepped bar. Now through this particular numerical, we have to compare. Please check your answer. The stress induced in the uniform bar is 99.02 and the strain energy stored in the uniform bar is 51.98 into 10 raised to 3. Please check your answers. And now we have to go for the comparison. That is comparison of strain energy. Comparison of strain energy. Therefore, strain energy stored in stepped bar divided by strain energy stored in uniform bar. So strain energy stored in the stepped bar, we have calculated how much value we got. 5.83 into 10 raised to 3 divided by whatever the value we have calculated for this. $51.98. Please check your answer once again. Whether 51 or 5 point something, 5.19. Please check your answer. Whether 51.98 into 10 raised to 3 or 5.19 into 10 raised to 3. Yes? Anyone please reply?
51.
51.
Sir,
It may be wrong, I think.
sir,
Yes.
लेंथ 300 घेतल्यावर
5.90 येते.
Length 300 आहे का? Just I will check. Yes, yes, yes. Sorry. So length is by mistakenly here in the statement they have taken the length 3000. Please consider the length. But if we'll check the length, yes, please do the changes here. By mistakenly he has written, that is, take the length 300 only. Instead of taking the length 3000, take the length 300 only. Then how much? Please check. 5.19, I think. Instead of taking the length 3000 for uniform bar, take this particular length as a 300 mm only. Then I think you will get 5.19 into 10 raised to 3. So this 10 raised to 3, 10 raised to 3, it will get cancelled. So what will be this particular ratio? Have you got 5.19 into 10 raised to 3? The length for the uniform
Yes,
section.
sir. 5.19 into 10 raised to 3.
Yes. Now put that particular value in this particular ratio and tell me this particular ratio. What will be the ratio? Strain energy stored in uniform bar, non-uniform bar or stepped bar, which is divided by, yes, 1.12. 1.12 means from that we can say that the strain energy in stepped bar is equal to 1.12 times strain energy in uniform bar. The strain energy stored in the stepped bar, which is equal to 1.12 times strain energy in the uniform bar. That means you can say that instead of taking the cross-sectional areas as a uniform or the plane, if we divide your component or if you prepare your component or the product in the form of stepped condition or in the form of non-uniform section, in the non-uniform sections, the maximum amount of energy will be stored. Because if you compare this particular figure, the stepped bar, it is having length 100 plus 200. The total length is 300 mm. The stepped bar is also subjected to the external load of 70 kilonewton, which is applied gradually. Their material is also same. If you compare the uniform bar is also having the length 300 mm. It is also subjected to the external load 70 kilonewton, which is also applied gradually. It is also made by the same material. But whatever the strain energy stored in the stepped bar, it will be the different, and the strain energy stored in the uniform, it will be different. And at the end, if we compare both the strain energies, from that we can say that the strain energy stored in the stepped bar or the strain energy stored in the uniform bar is more as compared to the strain energy stored in the uniform bar. Here you will get this particular factor. The strain energy stored in the stepped bar is equal to 1.12 times strain energy stored in the uniform bar. Therefore, if we prepare your section in the form of non-uniform section, in the form of stepped bar, the maximum amount of energy is stored in that particular section. So this is the meaning of this particular statement. Even load is same, length is same, material is same, but only cross-sectional areas are different. But how this particular cross-sectional areas or how this particular section, if it is also affects on the strain energy stored in this particular section. Therefore, from this particular statement, we can say that the strain energy stored in the stepped bar or the strain energy stored in the uniform bar is equal to, is more than the strain energy stored in the uniform bar. Okay. So this will be the last problem on this particular chapter number 2, that is strain energy type number 4, which is related to the strain energy for the bars of the varying cross-sectional area. Have you understood this particular part? Whatever the two problems we have solved, Whatever the two problems we have solved, in the first problem, the three sections are given. So we have to calculate the total strain energy. So we have calculated the strain energy stored in the each section 1, 2, 3, and at the end we have made the addition. In the problem number 2 also, the two sections are given. By using their forces, we have calculated the stresses. By using the stresses, we have calculated the strain energy stored in the section number 1, section number 2. At the end, we have made the addition. Then in the same statement, the case number 2 is also given, that is uniform section is given. For that also, we have calculated the strain energy. And at the end, we have compared it to each other. And from that comparison, we have observed that the strain energy stored in the non-uniform bar or stepped bar is more than the strain energy stored in the uniform bar. Have you understood this particular problem? Anybody is having any problem to understand this particular part? Yes? Have you understood this?
Sir, repeat kar.
Which one?
Sir, repeat kar.
Which part?
Starting person.
Okay. Okay, so this will be the figure. This will be the figure. Rohit, please understood. So in the type number, in the chapter number 1, we have solved the problem based on the bars of varying cross-sectional area. In that, we have calculated the elongation. If I have to calculate the elongation of this particular bar AC, if I have to calculate the total elongation of this particular bar AD, so what I will do, I will calculate the elongation of section number 1, I will calculate the elongation of section 2, I will calculate the elongation of section number 3, and at the end I will do the addition. Similarly, in this particular type number 4, we are calculating the total strain energy in this particular total bar. So here the section 1, 2 and 3, they are rigidly connected to each other. So if I have to calculate the total strain energy stored in the section AD, so I have to do, if I have to calculate the total strain energy in the section AD, so I have to do the addition, that is strain energy stored in the section AB, BC and the section CD. And to calculate the strain energy, we are having the common formula. U is equal to sigma square upon 2E into volume. So what we have to do, we have to calculate the separate stress induced in each and every section. Young's models will be remain same because all the sections are made by the same material. If I have to calculate the volume can be calculated by using the area of that particular section and multiply by this particular length. So this sigma means stress induced in each section. So in the section number 1, I can calculate the sigma 1. For section 2, I can calculate the sigma 2. For section 3, I can calculate the sigma 3. I will put the value of sigma 1, you will get the U1. I will put the value of sigma 2, you will get the U2. I will put the value of sigma 3, you will get the U3. U1, U2, U3 means U of AB, U of BC and U of CD. And at the end, I will do the addition of all the things, you will get the total strain energy. Similarly, whatever the first problem we have solved, in this particular problem only, we are having the three sections, section AB, section BC and section CD. So what I have done, the stress in the middle section, it is given 150 Newton per mm square, because stress is maximum where area is minimum. For the middle section, area is minimum, how much? 100 mm square. For section 1 and section 3, area is 200 mm square. So by using this particular 150 Newton per mm square, I have calculated the stress induced in the AB and CD. Baga. Maximum stress means area is minimum. म्हणजे sigma BC तुम्हाला दिलेला आहे का तर तिथे area minimum आहे. Okay, by using this particular 150 Newton per mm square, I have calculated the stress induced in AB and stress induced in the CD, and then by using the formula U of AB is equal to U of CD is equal to sigma AB square upon 2E into volume, I have kept the value. And then I have calculated the strain energy stored in the section 1, strain energy stored in the section number 3. Why? Section 1 and 3 are having the same area and the same length. Similarly, I have calculated the strain energy stored in the middle section BC, and at the end I have made the addition, that is U of AB plus U of BC plus U of CD. So this will represent the total strain energy stored in that particular section. Similarly, whatever the second problem we have solved, in the first problem, 3 sections are given. Now in this particular second problem, only 2 sections are given. Section number 1, section number 2. Okay, but for the calculation of stress, in the previous problem, stress values are directly given. But here, to calculate that particular stress, this 70 kilonewton force is given. So by using this particular 70 kilonewton force, I have calculated the stresses, that is sigma 1, sigma 2. By using the formula P upon A, stresses are calculated. I have kept that particular stresses in the strain energy. I have calculated the strain energy for section number 1. Similarly, I have calculated strain energy for the section number 2, and then I have made the addition. Total strain energy is equal to U of AB plus U of BC. So this will be the total strain energy for the non-uniform bar, that is stepped bar. Similarly, one uniform bar is considered. For this particular bar, total force is given, diameter is given. I have calculated the stress. By using that particular stress, I have calculated the strain energy 5.19 into 10 raised to 3. And at the end, I have made the comparison. So the structure of this particular numerical is same like a chapter number 1. But in chapter number 1, we have calculated the deformation. Total deformation is equal to delta L1 plus delta L2 plus delta L3. And we have used the formula delta L is equal to PL upon AE. Same structure is there. To calculate the total strain energy is equal to strain energy stored in the section number 1 plus section number 2 plus section number 3. And strain energy is a formula काय? Sigma square upon 2E into volume. So take the sigma of that particular section, volume of that particular section, and then at the end make the addition. You will get the final answer. Getting?
Yes, sir.
Okay. So now, rather than this, anybody is having any problem? Remaining others? Have you understood this particular type number 4?
Yes, sir. Understood.
Okay. What about others? Try to represent in your chat box so I can understood and I can go for the further. Okay, I hope everyone has understood. So with this, we have finished this particular second chapter also, that is strain energy. So in this particular strain energy, initially we have derived the basic derivation of the strain energy, sigma U is equal to sigma square upon 2E into volume. Then after that we have derived the 3 derivations for the gradually applied load, suddenly applied load, and the impact load. And after that we have solved the numericals based on the 4 types. The first type number 1 is based on the gradually and the suddenly applied load. Type number 2 is based on the kinetic energy calculation. And by using that kinetic energy, we can calculate the stress and the elongation. Then type number 3 is based on the stress due to the impact load. If the impact load is given, then how the stress, elongation, unknown weight, falling height will be calculated. And today we have discussed about the last type, that is type number 4, that is strain energy calculation for the bars of the varying cross section. So this will be the type number 4, and with this we have finished this particular chapter, that is strain energy.